Hello everyone, this is Charlotte Lei from the University of Macau, and this is talk for the CiPA Satellite Meeting and Calibrating 2021 meeting. I'm pretty sure that all of you may have heard of all models are wrong, but some are useful. So in this talk, what I would like to do is to draw attention to an important but perhaps under-addressed source of uncertainty in terms of model predictions, that of the uncertainty in the model structure or the equations themselves. And I will try to demonstrate this with a synthetic data studies example, showing that if we calibrate action potential models with what we usually think of as an acceptable range of misspecified ion channel kinetics, this can cause incorrect drop predictions. So let's get started. So first of all, is the model. In this talk, we're interested in cardiac electrophysiology or cardiac action potential models. So often dynamics of the membrane potentials is modeled as the following. We assume that the time derivative of the membrane potential is proportional to the sum of individual currents, Ij, and each current is then usually modeled in terms of three parts. First is the maximum conductance or permeability parameter, controlling the size of the current. So depending on the type of the current, sometimes it's called maximum conductance, while sometimes it's called maximum permeability. The second term is the dynamical term or the kinetics of the current. Either is modeled with a Markov model or a Hodgkin-Huxley gate model. And the last one is the driving term. Here is shown as an ohmic form, and which is proportional to the membrane voltage or membrane potential is Vm here, and sometimes it's modeled with a GHK equation, again depending on the current type. And in the rest of this talk, I will assume that we are mainly interested in the maximum conductance parameter, the G here. Next, I'm showing you a simulation of an action potential model by O'Hara et al. In 2011, using the same equation as well as the model parameters present in the original paper. Here I'm showing you the membrane voltage or the membrane potentials, the action potential itself, calcium channels, as well as the individual currents, including sodium, calcium, as well as various types of potassium currents within the model. And often after having a baseline model like is shown here, one might try to refit or tweak the model parameters to a particular applications. For example, modeling different cell types or some data coming from different experimental conditions, such as when drop predictions. And usually people do it by assuming the maximum conductance is the ones to be found for these different conditions. I.e., we try to find the size of each individual current or the contribution of each individual current for that particular applications. For example, a different cell type, like I said just now. And then after that, we use that to do various types of predictions. And when it comes to drop block predictions, for the purpose of this talk, I assume that we can just imagine it as simple as the predictions of if we get an X% reductions of a certain type of current, what would it do to the action potential? Right. So, but for the approach that I briefly described, it is usually based on the assumption that most, if not all, of the ion channel kinetics or the current kinetics, i.e. the shape of these curves here, are correct in this baseline model. Now the question is, are these models of ion channel kinetics or current kinetics reliable at all? So let's have a quick look at a few literature models that try to describe the very same type of current in particular, the IKR here, So what I'm showing you is the voltage clamp results of various literature models of IKR. And one is for the voltage clamp steps voltage, and then two types of action potential clamps. Now here is the results of these literature models predictions under these conditions, various conditions, and the colored line there all human ventricular models, IKR models. So IKR models from human ventricular models. And you can see they all look quite different actually. So they're not really lying on top of each other, and some of them might even show almost very different kinetics or dynamics under the action potential clamp here. And this one is HERC 1A from some expression systems. And again, literature model shows various types of predictions. And that shows, in fact, that's just reflecting how uncertain we are for this this particular IKR model in terms of the kinetics. So given the uncertainty, or given that we're actually not 100% sure what's the right kinetics for the ion channels or the individual currents, in the rest of this talk, I will try to show you the effect of such an uncertainty when it comes to drug block predictions if we just ignore these uncertainties. But before diving into these synthetic data studies that I mentioned, I'll take a step back and just talk a bit of some of the general terms as well as techniques that we use in this talk. Here, I'm just putting down some of the terminology that I use in this talk. I'm not trying to provide the definitions of each of the terms, but just the idea, the general concept, if you like, of what they mean. I'm not going to go through them one by one, but I'll put it, well, you can always pause the video and or refer it back to it whenever you want to. So I will move on and talk about the next thing is the prompt to inference schemes, or the techniques that we use when it comes to calibration or the use of the model, if you like. So first of all, we assume that we have a system Y, which is the action potential model in this case, which can be modeled with a set of governing equations F, and that takes a factor of parameters theta, which we want to learn through calibration. And then this model, it depends on some control variables, U in this case, or it can also represent the external applied conditions such as drug block predictions. And again, in the rest of this talk, I'll assume U is known and only theta is the one that we want to find. Or we want to learn through calibrations. So now it's naturally that we will split the use of the model into three steps. First is the calibration. The calibration is the process that we try to learn the features, the process of building the model, if you like. Assume that we have some data, experimental data Y under some conditions UC, YC and UZ, and then we try to infer the theta of the model based on these conditions and data. After that, we will do validation of the model using a different set of data, YV, and some different set of conditions, UV. And finally, we will use the model to do predictions, or if you like, contests of use, where we suppose we have some conditions, UP, where we can't really perform the experiments, and we want to use the model to do a model-based decision. So that is the split of the use, three stage of the use of the model. And then when it comes to calibrations of the model, we can calibrate the model using some statistical model with a full Bayesian treatment, for example. This is just one of the methods that we like to use, and and I will mention another method later, and later of this talk. With the statistical model, what I mean by that is, for example, we can assume the data YC is the model itself F plus some noise epsilon, and in this case we can assume we will assume some RID noise, Gaussian noise. So with this assumption and this statistical model, then we can write down the likelihood of observing YC, the data YC, given some parameter theta, which is given by this form here. And then the posterior of the parameter theta, i.e. the probability of the parameter after observing the data YC, is given by this Bayes rule, this expression here, which is the product of the likelihood and the prior of the parameter theta divided by some constant, which is also known as the marginal likelihood. To obtain or to approximate the posterior of the parameter, in practice, usually we would use techniques such as MCMC algorithm or a similar type to obtain or to approximate the posterior distribution of the parameters. And after obtaining the posterior distribution of the model parameters, we can use that to do predictions for some other conditions, for example, the UP, using this form here. So that is the calibrations that we will use when I show you the synthetic data example. Now let's talk about the synthetic data studies, the settings of this synthetic data studies. So like I said just now, suppose that we want to learn about the maximum conductance of each individual current or each current channel types by fitting the following parameters. The major type of currents of an action potential, cardiac action potential models, and while assuming the kinetics are known. So given this assumption that the kinetics are known, the obvious question to ask is do we need a good ion channel kinetic models, or do we need a perfect ion channel kinetic models? I'll put it in that way. So let's do a synthetic experiment by asking what if the current kinetics of the models are slightly wrong. So in order to do that, we will generate synthetic data with a ground truth model. Let's call it model T, which we will use in this talk. We will use the Tantosha et al. Model in 2004, and which is a human ventricular model. Obviously, we can pick another model, but we just take this one in the rest of this talk. And when we try to fit a model to it, we cannot use the same model because there's no discrepancy between it. So we will propose a candidate model, say, let's call it model F. We will use the Fink et al. 2008 model, which is again a ventricular, human ventricular model. In fact, this model F is based on the model T. So it's not the same as the model T, but very similar to model T, and only a few currents are different to model T. And those currents that are different to model T are shown here, which if you like, you can say this is the model discrepancy in this synthetic data study. And only 5 out of, well, however many, more than 10s in fact, however many currents in the two models are different between these two models, and the rest of the other currents, they're all the same between this model T and model F. And even for those that they are different, they're not drastically different. They are actually quite similar, but in some details that they are different. The biggest difference is, in fact, the IKL here. So with this model discrepancy in mind, let's have a look at how we're going to do model calibration for this synthetic data study. We will do that with 1 Hz pacing data with control condition, such that we will calibrate the model based on this only. And then for validation, we will use 2 Hz pacing data with, again, control condition with different frequency in terms of pacing. In theory, we should be able to tease out different dynamical property of the action potential model and see whether we can actually do validation based on that. And finally, for predictions, or if you like, the context of use, like I mentioned a few times already, we would do drop predictions. And in this case, we would try to predict a 75% reductions in IKR and see if our fitted model of the model F, the candidate model, can predict that well for the ground truth model, model T. And here it comes to the results of model calibration using the 1 Hz pacing data with 5 action potentials showing here. And the data, i.e. the synthetic data from model T is shown with the gray line here. And then the fit model with model F is shown with blue dashed line. And you can see that it's actually quite a good fit, I would say, if you imagine this is real data and we try to fit a model to that. Some might even say that's an excellent fit, depending on how robust you want model to be. But even with that, you can see a bit of discrepancy here, despite the some of the discrepancy in terms of ion channel kinetics. It can provide a good fit with some bit of discrepancy in the action potential chase. So this is a good fit, let's say, and then let's say we try to do validation with the 2 Hz pacing, and this is what it shows. Again, 5 action potentials, data showing gray, and then the blue dashed lines is the predictions of the model in this validation process. And you can see again some bit of discrepancy here in the action potential. But again, if this was real data, I wouldn't require, or I wouldn't ask for more than this. This is an excellent fit and excellent validation if it was real data. At this point or at this stage, one might say, okay, we have a great model and let's do model predictions with the context of use, say, predicting the 75% reductions in IKR, and we'll see what it does. And let's compare what it does between model T and model F. Model T, which is the ground truth model, the data is showing the purple line with 75% reductions or 75 block of IKR. And then the model F, the fitted model F, is predicting the red line here. It's actually not predicting well or it's not able to predict what the ground truth model is doing. So it failed. It's obviously failed in terms of the drop block predictions in this synthetic data study. Well, I mean, at this point, we can see that the problem is, that there is model discrepancy in terms of the current kinetics, and that by fitting just the maximum conductance cannot pin down the dynamical system based on what we used as the calibration data and the validation data. Well, some might even ask, is that just an issue with the calibration method, the full Bayesian treatment that we use? Well, let's try a different calibration method. We can use, for example, an approximate Bayesian computation approach, ABC, where we defined an error function. And with that, we will accept parameters when the parameters under this error function is less than some certain threshold delta. And let's say we pick some arbitrary threshold, say 0.1, and then we can solve this with genetic algorithm or with differential evolution algorithm. And with this ABC approach, this is the calibration results. The data is showing the blue line, and then the gray line or the black line, they are the accepted parameters predictions in this calibration process. And you can see they're all around, well, very close to the blue line. And then when it comes to validation, again, which is 2 Hz pacing data, it is still showing a very good predictions in terms of the validation of those some of the parameters found, but this is still acceptable usually. And when it comes to predictions of the context of use, even with the AVC approach, it's not able to predict it well. You can see the gray line is all over the places. So at this point, I would say this is not a problem with calibration methods, but it's really indeed the use of the calibration and the validation data, and with the kinetic assumption being correct, causes this issue here when it comes to drug block predictions. So as a conclusion, as the title implies, is actually the conclusions I would like to draw, as calibrating action potential models with misspecified ion channel kinetics can cause incorrect drug predictions. And then it leads on to 2 open questions, perhaps, is how do we choose validation data? The data that we picked is not able to pin down what we want to do as the predictions, and how wrong can these ion channel kinetics be in an action potential models for this type of applications. And that's all for today, this talk. And I'll just end it with this slides here as the acknowledgements, and thank you all for listening.